So this simple sum, which says cardiac output, which is in milliliters per minute, is equivalent to or equal to the heart rate, how many beats per minute, multiplied by the stroke volume, the amount ejected in each volume of the beat. So here we've got a diagram that shows you that there are things that can affect heart rate and there are things that can affect stroke volume. So heart rate is under autonomic innervation, so it's not under conscious control. We can't consciously make our heart go faster or slower without a lot of training. And then of course there are hormones that will influence the heart rate. One that comes to mind, of course, is adrenaline. Adrenaline, which is secreted from the adrenal glands which sit on top of the kidneys, causes the heart to beat faster. If we look at factors affecting stroke volume, we've got the end diastolic volume and the end systolic volume. And that we know that stroke volume is equivalent to end diastolic volume minus end systolic volume. And cardiac output, which is the end product, we get the amount of blood pumped out, and that is equal to, cardiac output is in 1 minute, the amount of heart rate and stroke volume in 1 minute. Let's talk a bit more about the autonomic innervation. So this is the nervous innervation, which is not under conscious control. So there are cardiac plexuses innervate the heart. So the vagus nerve, which is cranial nerve number 10, which we'll talk about a bit more in this topic, but more in 1005, and it carries parasympathetic preganglionic fibers to the small ganglia in the cardiac plexus. So the cardiac center is located in the medulla oblongata. So the medulla oblongata is up in the brain. And that has the cardiac acceleratory center, making it go faster, with sympathetic neurons, which increases the heart rate, and cardioinhibitory center, which controls the parasympathetic neurons, which slows the heart rate. So it's got both mechanisms to increase and decrease the heart rate. So cardiac reflexes, you've got that the cardiac center monitors the blood pressure, so baroreceptors in the blood vessels and in the heart, and arterial oxygen and carbon dioxide levels, or chemoreceptors. So the chemoreceptors are very sensitive to changes in carbon dioxide level. And the cardiac centers adjust the cardiac activity based on the blood pressure feedback and also the chemoreceptor feedback. So there's dual innervation, both from the parasympathetic and the sympathetic. So the parasympathetic releases acetylcholine, known, you see here as ACH, and noradrenaline, which we also know as norepinephrine. You'll find it in your textbooks as norepinephrine because your books are American, but you'll see it written in Australian and English as noradrenaline. And fine adjustment meets the needs of other systems. So here we have a diagram showing you the medulla oblongata, which is at the top of the picture. So this is in the brain. And then you've got another portion looking similar, but that's further down in the spinal cord. You can see the yellow bits that are coming off, which are the ganglia and the spinal nerves. So you've got the vagus nerve, nerve number 10, and you can see that it has both sympathetic and parasympathetic. Sympathetic is involved in speeding up the heart, and parasympathetic is involved in slowing the heart rate down. So together they have to work at maintaining a heart rate that we can live with and then respond to changes in our circumstances. So if we've got a lion chasing us, then we would want an increase in sympathetic innervation so that our heart beats faster. So the effect on the sinoatrial node means that the membrane potential of the pacemaker cells is altered. It's lower than the cardiac cells. So the rate of spontaneous depolarization depends on the resting membrane potential and the rate of depolarization. So here we've got a diagram showing you the normal resting and the heart rate, and the pacemaker cells have a membrane potential, and then you have to rise above that threshold in order for a heartbeat to occur. So the sympathetic and the parasympathetic are involved in stimulating the greater stimulation at the sinoatrial node. So acetylcholine, sympathetic stimulation, that slows the heart rate, whereas noradrenaline or norepinephrine is sympathetic stimulation, and that speeds up the heart. So here you've got parasympathetic stimulation, where we've got slower depolarization, and this will result in a slowing of the heart rate. While if we look at sympathetic stimulation, we've got the threshold being lowered and the heart rate is increasing. The atrial reflex is also known as the Bainbridge reflex, and this adjusts how the heart responds in relation to venous return. So if you've got more venous return, more blood coming back to the heart, that also will increase that will also trigger an increase in response to the sinoatrial node and an increase in sympathetic activity. You've also got hormonal effects on the heart rate. So an increased heart rate by sympathetic stimulation of the sinoatrial node will occur with, as I said, adrenaline or epinephrine, noradrenaline, and also thyroid hormones. Factors that affect stroke volume: you've got the end diastolic volume, the amount of blood in the ventricle contained at the end of diastole, the filling time, so the duration of ventricular diastole, and also the amount of venous return that is coming back to the heart. Preload is a complex concept for you to understand, but suffice to say it is the degree of ventricular stretching during ventricular diastole. It's directly proportional to the end diastolic volume, and it affects the ability of the muscle cells to produce tension. So end diastolic volume and stroke volume at rest. At rest, the end diastolic volume is low, the myocardium stretches is less, and the stroke volume is lower. If you then go and exercise, the end diastolic volume will increase, the myocardium will stretch more, and the stroke volume will increase. Frank Starling's principles of the heart is related to stroke volume. So as end diastolic volume increases, stroke volume increases. But this has physical limits. So it's limited by the ventricular expansion, by how much myocardial connective tissue there is, the actual cardiac fibroskeleton, and the how big the pericardial sac is. So that will limit the amount of stroke volume and how much it can increase. So end systolic volume is the amount of blood that remains in the ventricles at the end of ventricular systole. So this is after the heart contracts, at the end there will be a small amount of blood that remains in the ventricles. There are three factors that affect the end systolic volume. You've got the preload, which is the ventricular stretching during the diastole, the contractility or the force, which is produced by the contraction. So if you've got a sick old heart, then that's not going to be able to contract as much as a fit young heart. And then you've also got afterload, the tension in the ventricles produce to open the semilunar valve and eject the blood. Contractility is affected by the autonomic activity and hormones. The effects of the autonomic activity on contractility, if we look at that, if we look at sympathetic stimulation, such as with noradrenaline and epinephrine, it will cause the ventricles to contract with more force, and it will increase the ejection fraction, and it will decrease the end systolic volume, the amount of blood that's left at the end of systole. If we look at the contractility, this is under the control of the parasympathetic activity. Acetylcholine is released by the vagus nerve. The vagus nerve is number 10, and this reduces the force of cardiac contractions. Afterload is another concept, partnering with preload, and afterload is increased by any factor that restricts arterial blood flow. So if you've got aortic stenosis, then you can have an increase in afterload. As afterload increases, the amount of blood that can be ejected each time decreases. So this diagram also looks very complex. I'm not going to go through it in a lot of detail, but it is in your books, and there are a number of factors that will be affecting stroke volume. If we just look down at the bottom bit, the blue bit, you can see here that as end diastolic volume increases, so will stroke volume. If end diastolic volume decreases, so stroke volume will decrease. If we look over at the end systolic volume, if the end systolic volume increases, then the stroke volume will decrease and more blood will remain in the heart. If the end systolic volume decreases, then more blood will be moved out of the heart with each stroke volume. So in summary, the control of cardiac output is depending upon the heart rate and the factors that control that. So there's autonomic nervous system, both parasympathetic and sympathetic, circulating hormones, and the amount of venous blood and the stretch receptors. Stroke volume has control factors. The stroke volume is controlled by the end diastolic volume, the filling time, and the rate of venous return, and the end systolic volume is controlled by the preload, the contractility, and the afterload. Cardiac reserve is the difference between the resting and maximum cardiac output. So this is important if the person has got a heart with a degree of pathology. They'll be very interested in how much cardiac reserve the person has. So cardiodynamics, the cardiovascular regulation ensures adequate circulation to the body tissues. Cardiovascular centers control the heart and the peripheral blood vessels. Cardiovascular system responds to changes in activity patterns and circulatory emergencies. So here we've got a summary of factors that affect heart rate and factors that affect stroke volume. So again, I'm not going to go through it in a lot of detail. What we've got is that we know that hormones and autonomic innervation will affect heart rate, and we know that stroke volume, the amount that goes out with each heartbeat, is equal to the end diastolic volume minus the end systolic volume. And both of those, the heart rate and the stroke volume, will impact on cardiac output. So cardiac output equals heart rate multiplied by stroke volume. Okay, that's the end. We've covered a lot of concepts and a lot of information. I suggest you now go back over the notes that I prepared for you about the lecture and have a read through the pages that I've suggested at the top of the lecture notes. That's all from me. Bye.